First, average rate of change. If I drive to Las Vegas and I go 240 miles in 3 hours, what's my average speed? 80. And how'd you get that? You divided 240 by 3. Did it matter if I stopped along the way or if I even went backwards at some point along the way? Did any of that matter? No, I went 240 miles. It took me 3 hours. My average speed is 240 over 3. Okay, so here it comes, average rate of change. Your average rate of change generally is f of b minus f of a over b minus a. If I can show you this with a graph, let's say this graph is time and this graph is distance, okay? And here's 240 miles, alrighty, and here's 3 hours. I started here, I ended in Las Vegas there. How I got there doesn't matter. Oh, you're gonna stand? What? So, like, let's say we start off the trip and let's say I'm driving, okay? Doesn't it have the ability to zoom?
Yeah, but his head's in the way.
Oh, you mean because Axel's got like an unusually large head. Okay, I understand that. Okay, great. So I start off driving and you know, I'm going pretty slow. Then my wife takes over and she goes incredibly fast. And we get to Las Vegas in a jiffy. But the average speed is still 240 over 3. That is, the average speed is the slope of this secant line. Are you guys okay with that? The slope of the secant line joining the initial and final points ends up being the average speed, right? 240 over 3 hours, 240 miles over 3 hours, 80 miles per hour. So this doesn't have to be true just with distance versus time. It could be true with any quantities. Call this guy A, call this guy B, call this guy f of a, and call this guy f of b, right? And the slope of the secant is going to be f of b minus f of a, the distance from there to there, over b minus a, okay? And it wouldn't matter, like I have this graph going through the origin, just because we tend to think of home as being the origin, but it wouldn't matter, you know, no matter what your graph looks like. You know, if this is a and this is b, so that this guy here is f of a, and this guy here is f of b, then the average rate of change of this function is going to be the slope of the secant joining the initial and final points. That is the slope of this blue line, f of b minus f of a over b minus a. And I want to say again, the axes could be anything. I mean, if I wanted to get the rate of change of inches of grass growing, you know, versus inches of rain, or inches of water, I guess, but I'll say rain, alrighty. Well, you know, if my grass, no matter what my grass did, if from here to here is 5 inches, and from there to, of grass growth, and from here to here is 10 inches of rain, then the average rate at which my grass grows is going to be 1/2 inch of grass for every inch of rain. You see what I mean? I'm hoping you see that when you graph a function, the slope of the secant line joining the initial and final points ends up being the average rate of change of the function. And I keep referring to this line as the secant line because that's the general term we use for a line that joins 2 points on a graph. It comes from this idea of what you learned in geometry. Remember in geometry that if you have a line that touches a circle at one point, we call this line a tangent. But if you've got a line that touches a circle in 2 points, and remember it's a line that goes on forever, then we call that a secant. You guys remember that? Well, no, okay. But we pretty much apply this terminology to graphs. Even though this is obviously not a circle, but still it's like a line that's just cutting through the graph, like the way a secant cuts through a circle. So another definition, or another another name for the average rate of change, which is given by this formula, is the slope of the secant. slope of secant joining the points A comma f of A and B comma f of B. You see what I mean? So that's our average rate of change. So let me see what I want to do here. I'm not going to do that. I'm going to do this. Example number 1. Get average rate of change of f of x equals x squared minus 4 from x equals 1 to x equals 3. Okay? So this is the problem I'd like everyone to do. And how are you going to do it? Hey, find what the x and y are at x equal 1, find what the x and y are at x equal 3, and then plug into that formula. Just get the slope of the line joining them. Good luck. I'll give you 60 seconds. So Leilani, are you able to learn while you're doing that?
Yeah.
You are really? I can't
Auditory.
Huh?
Auditory. Everything I learn.
Oh,
auditory.
really? You're auditory? Oh, good for you. I'm totally visual. So if I was doing what you were doing, I wouldn't learn a thing. This would all be just nothing. Hey, anyone get an answer yet? What'd you get, Daniel? Smartest guy in the class. 4. Daniel get 4. Anyone agree with him? Oh, good for you guys. Okay, good for you. Yeah, 4 is good enough. You know, average rate of change is going to be f of b, which is, what is that? 9 minus 4, which is 5, minus f of a, which is negative 3, over b minus a. And so you end up with a 4. Good. Yeah, and that's it. That's average rate of change. Any questions or issues? Alrighty, then let's turn our attention to instantaneous rate of change. I just heard someone say yes. You guys are funny. So, considering my trip to Las Vegas, right? In 3 hours, I went 240 miles. So I started there and ended there. But the fact is, I didn't go 80 miles an hour for every moment of this trip. You know, some of the time I'm going slower, and others of the time when my wife starts driving, I go way, way faster, uncomfortably faster, scarily faster, okay? And so the instantaneous rate of change is different along this entire trip. You see what I mean? Also, you'll notice if we switch drivers, what would you expect to happen to this graph?
Go down to 0 for a second.
Well, no, not the position. I didn't suddenly go home.
It'll go flat.
Yeah, it'll go flat, you know. So, I mean, I'd expect if my wife and I change drivers, you'd expect it to go like this and then go flat, and then my wife takes over. So you can see what we did was we actually changed drivers while in motion. We just put it in autopilot or whatever you call that. What is that called? What's that? Yeah, cruise control. I could not think of the term. Yeah, we put it in cruise control, and then she goes over me, I go under her, and then we switch, and it works out just fine. Okay, great. So you can see, like right here, you know, we're not going that fast. You can tell we're not going that fast because we're just not making a lot of progress. Here, we're going extremely fast. Well, how do I measure that? I mean, I can look at the speedometer. When I'm driving, the speedometer says 60. When my wife drives, it says 90 or whatever. You know, at some point, my speedometer stops working. You know, but how can I look at a graph and get how fast we're going? Well, you're still going to get an average rate of change, but you're going to do it for 2 points that are, yes, Andrew?
I was going to say slope of the tangent line.
Yeah, that's exactly right. So many of you remember that from last year, the slope of the tangent line. That is, I'm going to get an average rate of change, no different than here, but it's going to be the average rate of change over an incredibly small period of time, which is, as I told my AP Physics class earlier this year, that's the way your car actually gets your speed. Your car, when you look at the speedometer, it's not telling you your instantaneous rate of speed. It's not telling you what your speed is at that moment. It's actually giving you an average speed during the time of one revolution of your wheel. You see what I mean? So that's the sort of thing I'm going to do. I'm going to say, I want the instantaneous rate of change right there. Well, then I'm going to get the average rate of change for 2 points that are really, really close together there. That is, I'm going to say, okay, I'm going to call this guy, just 1 second, I'm going to call this guy A, and I'm going to call this point A plus H. That is just a smidge more than A. So that this point here is f of A, and this point here is going to be f of A plus H, right? This y-coordinate is f of A, and when I move over a smidge to the right, go A plus H, then this guy's going to be f of A plus H, all righty? And I can get the instantaneous rate of change. And by the way, I feel so bad, maybe because I'm stressed about being videoed, but I forgot to actually define instantaneous rate of change. Because many of you may not have the sense of what that is. Instantaneous rate of change. And what that is just 1 second. Oh, on my notes, I don't really define it. Well, your rate of change at one point in time, your rate of change at a point in time. It's essentially what your speedometer is telling you. Just a second, let me get a picture. Okay. And with average rate of change, you're essentially using your odometer and your clock. You use your odometer, it says 240 miles. You use your clock, it says 3 hours. Then your average speed was 80 miles an hour. But with instantaneous rate of change, you're using your speedometer. It's telling you what your rate of change is at that moment in time. Okay, great. And so, let me get to my notes here. And so I'm going to get the instantaneous rate of change, by just getting the slope of this line here. Getting the slope of the line joining these 2 points that are really close together. That instantaneous rate of change is going to be f of A plus H minus f of A all over H. And then, because I want these 2 points to be as close together as possible, what am I going to let H get closer and closer to? 0. Many of you may remember that from last year as well. I'm going to let it get close to 0 so that these 2 points are really, really close together. So I get the limit as H approaches 0 of f of A plus H minus f of A over H, which is going to get me the slope of the tangent line. So if you're thinking graphically, your average rate of change is the slope of the secant line, and your instantaneous rate of change is the slope of the tangent line. If I wanted to get the instantaneous rate of change when my wife is driving, then I'd have to choose a point really close to her, a second point really close to her. This would be A, and this guy would be A plus H. So that this guy would be f of A, and this guy would be f of a plus h. And then again, I would let h be closer and closer to 0, so that those 2 points are getting closer and closer to each other. So pretty soon they're virtually on top of each other, and you're getting the slope of the tangent. Any questions or problems on this? Then let me do a problem, and then I'm going to have you guys do a problem, and then we'll probably be done. Oops. Alrighty. Here, example number 2. Get instantaneous rate of change of y equals x squared minus 4. That's the graph I had last time, or f of x equals x squared minus 4 at x equal 1. What they're asking for is the slope of the tangent at x equal 1. The slope of the tangent at x equal 1. And I am now going to plug into this formula. That's going to be the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. That is my a is 1 in this case. And then, this guy is equal to f of x. And now I'm going to stick 1 plus h into this equation, and I'm going to stick 1 into this equation, and then I'm going to do some algebra. Here we go. Limit as h approaches 0. Stick 1 plus h in here, and I get 1 plus h squared minus 4. Minus, stick 1 in here, and I end up with negative 3. Are you guys okay with that? So I stock 1 plus h into the equation, and then I stock 1 into the equation. And I got what I have there. And then finally, this is h. Is there anyone in this class that has never seen this before? So they teach this in college prep trig as well? Do they? Anybody in here from college prep trig last year? I forget. And then Kylie, in your summer class, did they do this? Okay, cool. Then maybe everyone's on board. Maybe it's all good. Well, anyway, let's go ahead and do some algebra. I got the limit as h approaches 0 of 1 plus 2h plus x squared minus 4 plus 3 over h. So you notice I got 1 minus 4 plus 3, which makes 0. So I end up with the limit as h approaches 0 of 2h plus h squared over h, which means I get to factor out an h from the numerator and cancel the h's. So I got the limit as h approaches 0 of h times 2 plus h over h. And so the h's cancel. And then as h gets closer and closer to 0, this guy gets closer and closer to 2. So I get 2. So I want you to see that although the slope of the secant between 1 and 3, the slope was 4, it turns out the slope of the tangent at 1, which is this line here, okay, the slope of the tangent at 1 is only equal to 2. Because I'm not getting the average from 1 to 3, I'm just getting the instantaneous rate of change at x equal 1, and that ends up being 2. Any question or issue on this? You guys ready to do one on your own?
Yes.
All right, here it comes. Should I do a cubic? Should I do 1 over? going to have you guys plug it in, and then we'll go from there. For f of x equals 1 over x, get instantaneous rate of change at x equal, let's say 2. Good luck, you guys. Set it up. The algebra might be too difficult for you because it involves a complex fraction. But see if you can set this up. Boy, I'm so bummed about my stupid camcorder. I spent $20 for a new battery too, and it looks like it did no good. Down the toilet. Hopefully everyone's starting with that, just the basic definition of the slope of the tangent. Getting the slope of the secant between 2 points, but then letting that second point get really, really close to the first point. And then let's go ahead and plug in. Oh wait, it's 2. Okay. Did you guys write that down? If you did, then you're good. I mean, you're 90% of the way there. Now let's go ahead and plug it into the formula. So my formula is 1 over x, so this will be 1 over 2 plus h minus 1 over 2 over h. And then at this point, you've got a complex fraction, a fraction with fractions inside of it. You know, here's a fraction, there's a fraction, but this is an entire fraction. And the way you deal with complex fractions is you multiply top and bottom by the least common denominator of all the denominators. So I've got 2 different denominators. I've got 2 plus h and I've got 2. So the least common denominator between 2 plus h and 2 is going to be 2 times 2 plus h. And of course you'll never go wrong by just, you know, taking all of the denominators and just multiplying them together and using that as your multiplier. But regardless, I'm going to multiply top and bottom by this equation by 2 times 2 plus h. How many people remember learning this in your past? How to simplify? Okay. Because this is something that, you know, it seems like Algebra 2 teachers don't hit this very hard anymore. And yet it's a real important skill to have. But you know, the last several years, my calculus kids are almost incapable of doing this, which tells me that it wasn't taught to them in second year algebra. Okay, or IM3 or whatever they call it nowadays. Okay, so the 2 plus h cancels and I'm left with just the 2. And for these guys, the 2's cancel and I'm left with just the 2 plus h. And then here I've got 2 times 2 plus h times h. And this is the limit as h approaches 0. Don't forget that limit. That's incredibly important. You're getting the slope of a tangent, not a secant. So I got 2 minus 2 plus h, so that gets me negative h on the top. 2 times 2 plus h, h. And so you see the h's cancel. and I've got the limit as h approaches 0 of -1 over 2 times 2 plus h. And now I can let h go to 0 and I get -1/4. That's it. That's the slope of the tangent at x equal 1. If I were to graph this guy, here's 1, 1, okay, and this is a hyperbola that goes like this, then the instantaneous rate of change at this point, which is the slope of the tangent at that point, would end up being -1/4.